Okay, so hello everybody, and actually I'm very happy that you invited me to this workshop. Thank you very much, George and other organizers. And also it's very good that Julia has spoken before me, because then now I can use every of his, formalism and work he did with you. And so I decided to give you a joint talk of two papers, one that we did with Julia, and then we had a follow-up result, so that I will present mostly now. Okay, so for the motivation, actually, this will be kind of repeated thing from Julia, because so we are interested in temporal graph. This is because it's important for weblogs, for analytics, in human activities. We can use it for customer relationship management, for business intelligence, or even for criminology, because at some point when you want to investigate the things, you can be interested in timed interaction between people, right? So this is what we are interested in when we study temporal graphs in general. In our context, we are more interested in co-working session, actually. And so this is how we came to define this notion of temporal matching that Julian has did a very nice presentation to you. Okay, so I did some drawing, some terrible one, but anyway, what I try to tell here is that when we study temporal graphs, we can have this vision of how to say getting a graph and then repeat it several times. This is when there's no changes, and this is a kind of a constant link stream. Well, I call it link stream, but it's the same as the temporal graphs. Okay, good. And here, if we look at the problem of matching, then it's just kind of boring. And Julian explained you why about this, so I will skip these slides. What I wanted to say is that in real world data sets is much more messy. It's something like this, okay? And our way to view it is that in this kind of time interactions between people, we would like to compute the number of collaborations of a minimum duration. So all this blue that I draw here has to have a minimum length, and now we did a big mistake. We called this length gamma, and oh my God, I don't know why we did that, but I'm sorry we did that. Okay, so in this is the kind of informal presentation of what we are interested in. I will give you a very formal slides now, and I hope that we can go through it quickly. Most of this formalism has been said by Julian, so I will try to do it very, very fast. So to us, a temporal graph, which we also call it a link stream, is a trip, T, V, and E. So T is a set, a discretized set from 1 to some number tau, representing time instance. And this is important for us. Then we have a V as the set of vertices, and what we call temporal edges will be a pair of made of one time instant and one edge. So classical edge is in graph theory, UV. Okay, here what we consider as a gamma edge is a set of repeated edge. This is also important, and I will draw I will show you a drawing right after, so that we can have the intuition for it. And now the problem that Julian and I were interested in is it's a bit of independent set, actually. It's independent gamma edge set. So we define this gamma edge, and then we draw it like this. So here I gave you two drawing. I will explain it later on. But what is important in these two drawings is that all the blue and the red squares are two edges. It's with gamma being equal to 2. Why is it? It is because, so for example, I take this one guy example. It's an edge between C and D repeated twice. So this is why we call it the gamma edge. Okay, so good. So this is the definition of the gamma edges. Now we want to compute the gamma matching. That is a collection of gamma edges that will not touch each other somehow. So it's really like a independent gamma edge set. Okay. And here, why I did this drawing to you, it is because if you do greedy algorithm, if you go from here on the left-hand side, you go from the first time instance to the last time instance, you will pick the blue squares drawn here. So at the end, you end up with 3 independent squares. So it's nice. You have a solution of size 3, and you are happy. Now, if you look at the right-hand side example, it is exactly the same link stream, but if you go, how to say, in reverse order of the chronology, so you start at the last time instance and you go to the first time instance, you can kind of build a gamma matching of size 2. So these two blue squares that I draw here, and you are less happy, right? Because you would like to maximize it. Okay, so so far so good. So our question is to compute a maximum set of independent gamma edges. And so formally we define the problem gamma matching. I give the decision version, so with an integer k, and we want to compute a Boolean stating if there is a gamma matching in L of size k. So we prove that the polar is NP complete for gamma strictly bigger than 1, and then measures Moulton, Idemaya, Tamaraev, and Josa, you prove a very much stronger property on this, which implied also NP-completeness for very, very restricted link stream. And I want, I don't want to go into the detail, but really it's like if you take the underlying graph, so this is the graph of all snapshots, and it's only a path, then it's still NP hard. It's still NP complete. So really the poly is very, very hard. Actually, we don't really like hard problems. So we would like to give some kind of result that we can use somehow. And this is what motivated the 2 approximation we did with Julian, and also the kernelization that Julian presented to you. But now what I would like to present today is mainly two results on the theoretical side, this one and this one on the theoretical side, and then on the applied, how to say, for numerical analysis, I would like to recall the implementation we did following Julian work, which is given here. I will send you the PDF, and it's clickable link, so you can go directly to the implementation. Okay, so this is the first one, is the old one, and the new implementation is this one for the two results in the field that I wrote in the field. It was coded by Timothy Picape. Okay, good. So what I would like to do now maybe is to give you some idea how we obtain our two main results here. So the first one is a DP, so a dynamic programming, computing exactly a gamma matching with a big runtime. So it's not polynomial, right? It's I use this O star notation to say that I forget about the polynomial factor. So if we forget the polynomial factor, the leftover runtime is gamma plus 1. You will see why is plus 1 to the n. It will give you an exact gamma matching. So this algorithm, when we run the computation, it takes a lot of time. Okay. Then for the second result is a PTAS, so polynomial time approximation scheme. Is available for spatial link streams. We couldn't get it for the general case, and I would try to give you the intuition why we couldn't get it for the general case and how we can use it for this geometric case. Okay, good. So let me start with the DP. So the idea for the DP is the following. So the idea of the DP is that if you take a link stream, so this one exactly the one that I showed you before, the first example. For the DP, what we should store in the table here, in the general case, is in fact we have this size of the matching, the delta edge, right? The gamma edge, sorry. So the gamma edges has their thickness in the time dimension is exactly gamma. So the main idea here is that you can just use a sliding window of size gamma. So here in my example, gamma is equal to 2. That's why my sliding windows. Sorry. So this is my sliding windows. Okay, sliding window. I will take it of size 2, and then if I can record all the apparition of the temporal vertices here, then I have all the informations. But then my DB table will be very, very big. It will be something like gamma times 2 to the gamma times n. So in order to reduce this, the idea is that for every vertex, we store only the last use position, because then we really don't, we only care about the last use. So in this example, for vertex D, let's say I don't want to use it in my sliding window and at all. So this is why I put X on its position, okay? So for D, we don't use it in the sliding window, so we put it X here. For C, we plan to use up to 2. So this is why we put a 2 over here. For B, it's the same situation, and for A, it's like with D. And so if we do this, if we choose all these yellow vertices, then actually the only gamma matching that we can build like this is exactly this guy. So this is why the value will be just 1 in this entry, okay? And it's DB entry. So I would take another DP entry and just I would like to show you that, yeah, here, for example, this is another DP entry. I put 1 to everybody because actually I plan to go up to the first position of my sliding window. And so here, the result is 2 because actually we can choose this 2, okay, among the yellow vertices. Okay, so this is the main idea of the DP. On the entry, we only need to choose the last position or X when we don't use. So the number of position for each vertices that we have to record is gamma plus 1 for this X. And we need to do this for every vertices. And that is why our DP table has size gamma plus 1 to the n. Okay, so this is very nice, good. And this is the main idea for the DP. Now, I show you for the geometric, for the PTAS. So the result for the PTAS, I will just, first, I have to define what I call the geometric link stream. Then I give you the intuition for building the PTAS, and then that's all, actually. And then we go to the numerical analysis and we conclude the talk. So the idea for the geometric link stream is this. If you are familiar with a unit distance graph, then it will be very fast for me to tell you what it is. So here, for example, here I have what we call unit disk graph. So we have a unit disk in a plane, and we put edges between the disk when they are touching, when they are intersecting. So here, for example, okay. So this geometric model will translate into this intersection graph. So A and B are disks that are touching, and C and D too, but they don't touch each other. Okay, so if I do this for every time instant, then I will have what I call a geometric link stream. So here I have a moving vertices somehow, and then at first instant A, B are touching each other. Oh, sorry, this is a mistake. Okay. It should be like this. Okay. At the second instant, C, D are not touching each other anymore. So this is why we only have the edge between A, B. And at the third instant, we have a click between A, B, C, and then D is just touching C. Okay. So this is what we call a geometric link stream. We have to define some extra parameter, which is called velocity and density. This is very inspired from geometry. Why do we do this? Actually, we do this because now you see that we not only we can build the DP, the sliding window with the temporal dimension, but we also can do this with the geometry dimensions, so X and Y. So this is essentially the idea for the PTAS. So on the time dimension, we do the sliding window like what I just explained to you before. And then inside each time instant, so inside each snapshot, for controlling the geometry, we use the linear path with dynamic programming on kind of stripes of the plane. So we are cutting the plane into stripes, and then we use what is done with a path width on independent sets, actually, and we get it like this. Okay, so now let me conclude in this last slides. We have still 3 slides that about the numerical analysis. So the situation here is we have a DP, which is exact. So the approximation ratio is 1 because it's exact, okay? But it's long, it's very, very long. We have a PTAS, and the PTAS only work for geometry case. The approximation ratio that we computed for some of our data set is between 1.3 and 1.4. So, Okay, we build some artificial data sets that we expect that the PTAS approximation ratio is about this. And then we have this greedy algorithm where the approximation ratio is 2. And Julian explained to you why it's 2, right? Okay, so I don't have to explain it. I just show you how we compare this. So when we read these kind of numbers, we will think that, okay, greedy is bad, right? It's only fast and bad. And PTAS is slow but good, right? Because the expected approximation ratio is bigger. Well, the thing is that we run it on some data set that we generated. Really, we choose all the parameters to favor the PTAS. And what you see here is that it's not so the case, you know, because okay, for the first 3 data set is okay. So for the first 3, the PTAS is performing very well. But for this one, see that the grid is performing very well. So here is the mean of the outputted size of the gamma matching. And here we cannot explain this. Why? I mean, the greedy is expected to have approximation ratio 2, and our PTAS is expected at 1.3 or 1.4, somewhere about this. Okay, so this is not expected. And then what we thought is that maybe actually the real ratio is not what we expected. You know, maybe this one is not 2, but this one is something like 1 point, very close to optimal. Why not? You know, 0.5, for example. I don't know. But the thing is that we don't know the exact answer. And so that's why we have to run the DP that I explained to you. Okay, so now for some of these instances, we can run the DP.
Bing, can we conclude in, let's say, 1 or 2 minutes?
Yes, because we are in the next to last slide.
I very much like what you said. I didn't want to interrupt you, but yeah.
Okay, don't worry. We are coming to the conclusion now. Okay, so to conclude, so we compare the ratio of the greedy and the PTAS with the DP, and actually you can see here that the ratio is really close to optimal. And really it's 1.02 on our data set. And this is actually quite nice. So even the greedy is performing very well. And so for the last slides, what I wanted to say is that we also do some run on the real world data sets. And actually on the end run that Julian explained to you, it performed very well. On the roller net is less well. And Julian also explained to you what means the roller net already. Okay, so actually basically this is our results. I invited you to check the link on the GitHub for the implementations. For open question, actually, I already did that to some among you. What I really wonder is that, can we do better for the DP? Because at the moment we have this time for the DP, but I really hope that we can do it with in time 2 to the end. And this is the end of my talk. Thank you very much.
Thank you very much, Bing.